Have you ever stopped to think about energy? I mean, really think about it. From the jolt of caffeine in your morning coffee to the massive grid that powers our entire civilization, our world literally runs on it. But underneath everything, there are these invisible laws, these hidden rules of the game that control how it all works. And today, we're going to pull back that curtain and take a look at the fundamental physics governing it all.
So, let's dive right in with a question. And it's about something so simple, so everyday that you've probably never even thought to ask it. But the answer? Well, the answer reveals one of the deepest, most fundamental principles of the entire universe. You know exactly what I'm talking about, right? You make a hot cup of coffee, you put it on your desk, and you get distracted. Inevitably, it cools down, and the air around it gets just a tiny bit warmer. But have you ever seen it happen the other way around? Has a room ever gotten just a little bit colder because it decided to pour all its heat into your cup and make it boil? Of course not. So why not? Why does energy seem to be on a one-way street? To solve this little mystery, we can't just shrug and say, well, that's just the way it is. Nope. We need to dig a little deeper. We need to get into the nuts and bolts of how energy, specifically heat, actually gets from point A to point B. Okay, first things first, we gotta understand what heat actually is. And here's the deal. It's not a thing. It's not a substance. It's just energy on the move. And that energy has three main ways of getting around. If we can understand these, we're one step closer to cracking our coffee code.
First up, we've got conduction. This is basically heat transfer by touch. Super simple. Picture this. You stick a metal spoon in a piping hot bowl of soup. What happens? The super excited, jiggling particles in the soup start bumping into the particles in the spoon, making them get all excited and jiggle around. It's like a chain reaction that travels all the way up the handle until, ouch, you feel it. That's conduction in action.
Next up is convection. This one is all about movement in fluids. So think air or water. The classic example is a pot of boiling water, right? The water at the bottom gets hot, it expands, becomes less dense, and shoots up to the top. Meanwhile, the cooler, heavier water at the top sinks down to take its place. You get this rolling, circulating current of heat. It's the exact same way a space heater manages to warm up an entire room.
And finally, there's radiation. Now, this one is kind of the rock star of the group because, unlike the other two, it doesn't need any stuff to travel through. It can move through the total emptiness of space. It's pure energy just beaming out as electromagnetic waves. It's how we feel the sun's warmth from, 93 million miles away. And it's that warmth you feel on your face from a campfire, even when you're not in the path of the rising hot air.
All right, so now that we know the three ways heat gets around, we are ready for the first big rule of energy. And to get our heads around it, let's do a little thought experiment. It's a fun one, and I promise the answer is going to surprise you.
Now really think about this for a second. Your gut instinct probably tells you the room is going to get colder, right? I mean, it's a refrigerator. Its job is to make things cold. Or maybe nothing happens at all? What's really going on with the energy in that room?
Okay, are you ready for this? The answer, and this totally messes with your intuition, is that the room gets warmer. Yep, warmer. See, a refrigerator is basically just a heat pump. Its job is to move heat from the inside of the box to the outside. But, and this is the absolute key, the motor that does all that work uses electricity, and that whole process generates its own heat from those coils on the back. So while you're moving a little heat out of the fridge's interior, you're actually pumping even more heat into the room from the machine itself.
And this little refrigerator puzzle is the perfect illustration of the first law of thermodynamics. This is one of the most fundamental ironclad rules in all of physics. It's the law of energy conservation. And it's pretty simple. Energy can't be created and it can't be destroyed, period. All you can do is change it from one form to another. In this case, from electrical energy into heat.
But wait a second. If energy is always conserved, if the total amount never changes, that still doesn't explain our coffee. The first law says the amount of energy is constant, but it doesn't say anything about the direction. Why does it have to go from the hot coffee to the cold room and not the other way around? Well, to figure that out, we need to introduce a totally new idea. The idea that not all energy is created equal.
Let's use an analogy to make this super clear. You've got two people, Andy and Wendy. Andy has 10 friends. Wendy only has 5. So on paper, Andy has more friends, right? Quantity-wise, he wins. But Andy's friends are kind of flaky. Wendy's 5 friends, though, they're rock solid. You can count on them for anything. So who has more valuable friends? It's Wendy, hands down. Well, energy works the exact same way. The total amount of energy might be the same, but some forms of it are just way more useful, higher quality than others.
And this, right here, is the absolute crucial point.
While the quantity of energy is always conserved, its quality is not. Every single time energy moves or changes form, a little bit of its usefulness just disappears. It degrades. It turns into a more scattered, less useful form. And that form is almost always just low-grade heat. Now, physicists have a word for this measure of messiness, this randomness. It's called entropy. And this brings us to the mighty second law of thermodynamics, which is basically the universe's messy secret. All it says is that the total entropy, the total messiness of the universe, is always going up. Things naturally go from organized to disorganized. An egg in its shell is neat and tidy, low entropy. A scrambled egg is a chaotic mess, high entropy. And you know you can't unscramble an egg.
And that, right there, is the answer to our coffee mystery. Finally, the concentrated, useful heat energy packed inside your mug, that's an ordered, low-entropy state. The random, disorganized heat floating around the room, that's a disordered, high-entropy state. And the universe is just hardwired to increase the total mess. So that orderly energy in the cup has to flow out and spread into the room to create more disorder. It's not just a tendency, it's a statistical certainty.
So the universe is constantly trying to get messier, and high-quality energy is always degrading into low-quality heat. Now that might sound a little bit depressing, but here's the twist. This exact process, this unstoppable slide towards disorder, is what we've managed to harness to build our entire modern world.
Seriously, every power plant, every engine, every turbine is basically an entropy surfing machine. They're all cleverly designed to sit in the middle of this natural flow of energy from a high-quality state to a low-quality one. By managing that flow, we can skim off a bit of that energy and make it do useful work for us, like generating electricity. But the second law also puts a hard limit on our efficiency. Let's take a typical car engine. Of all the concentrated chemical energy stored in the gasoline, what percentage do you think actually gets used to turn the wheels and move the car forward? The answer is a pretty shocking 24%. That means the other 76% is converted directly into low-quality, disordered heat that just radiates away into the atmosphere. And this isn't just bad engineering we can eventually fix. This is a fundamental tax imposed by the universe. The price of doing useful work is that you must always increase the total entropy, and that means generating waste heat. There's just no way around it.
So, we end up right back where we started. The first law says energy is never really lost, but the second law reminds us that its quality, its usefulness, is always fading. The big question these hidden rules leave us with is this: now that we understand the game, how do we play it more intelligently? How can we design our systems to waste less of that precious quality and make the most of the energy transformations that power our world?